University of North Dakota for a postdoc in a quantum optics group. So, as I said, that we are doing completely the experiments. So, two things are required. So, one is the manpower. This is the manpower what we have, and another one is the funding. So, right after my joining here, University of Hyderabad, I have approached about all the 6 to 7 funding agencies. They have funded with a decent amount. With this amount, we have established the facility. I must thank these funding bodies to kind of giving a faith on our ideas and establishing the facilities. So first, I will, at a glance, I will show our facility, what we have at the University of Hyderabad. So then I will discuss each in detail, what is the purpose of that facility and what is the aim of the whole lab. So before we start the experiments, basically we have a computational facility. So in order to utilize the experimental resources in an efficient way, so first we design our all the nanophotonic structures using the numerical software, so that we can optimize the parameters and we can get the optimized parameters in the experiments. And we have established a very compact clean booth it is very in contrast to the conventional clean rooms where you have to spend really much more money. But in our case, we are able to manage within a few lakhs with this clean booth. The idea is that the systems or the structures which we are working is in the order of 1 by 100 of our human hair. So therefore, we need to really maintain the cleanliness condition. Otherwise, we are kind of destroyed all the properties by the dust and all the other particles. Therefore, we established the clean booths. And also, since, as I said, that to manipulate the single photons or the single emitters efficiently, so we need a nanostructures. So we established the facility, which is a fiber fabrication facility. You can see that. So the conventional single mode fiber is going to become a nanofiber. So it's a unique facility in the country. We have it. So many people are trying to access this facility and utilizing for their own research purpose. So as of now, it is functionalized and it's working since 2 years in our lab. So, and this is the nano positioning stages are required because the nanostructures should be manipulated, and it should be kind of moved from the one location to the another location to do this single photon manipulations. So we have a nano positioning stages, and we need an inverted microscope, which is this is also a very expensive microscope where you can kind of see the micro or the nano manipulation from the downside, and the top side you can sort of have a just wait. So on the top side you have a sample, and also you have a micro manipulator on top. Then from the bottom you can view the all the manipulation process. And in order to generate a single photon, so we need to have a control of very precise in the fluid dynamics. So we developed a micro nanofluidic technique to pick up the single quantum emitter from the solution. Often most of the people work with the ensemble of quantum emitters, which is not the classical source of light. So therefore, we developed a micro nanofluidic technique where you can really isolate a single quantum emitter. And in order to judge whether you have a single photon source or the classical source, so one must perform the photon correlation measurements, and that's the Z2, which is the intensity correlation measurement. So we developed in our place that is a setup which is it's a very compact, so it is a movable from one place to another place. This is the 2 single photon counters, and this is the Hambre boundary setup, what it's called. We have established and customized setup, and also not only the timing information of the single photons which is coming from the sources, and also you need a spectral information, because in real quantum application you need a indistinguishable single photon source. So the single photons should be indistinguishable. So that means that in order to say the spectral line width of a single photon, you need really high sensitive spectrometer. So this is the single photon to do the single photon spectroscopy. So we have established this facility. At a glance, I gave you the facility what we have, and let's start the talk with the introduction. So as proposed by the Jeff Kimball from the Caltech sometime back, that if you have a single atom trapped in the microcavity and it can work as a single photon source, and the same system if you have in another place, they can talk each other through the free space. So as a result, you can make a one system as a node, another system as the node B, then they connect, they can talk each other and efficiently manipulate the single quantum states. So then they can make a quantum network of photonic domain. So in such quantum network, so if you have a single photons coupled in a fiber platform, so you can be useful for the like a such photonic systems if you have, then you can use it for the quantum computation. So that was the proposal, theoretical proposal was proposed by the Jeff Kimball some time back, and let's see how to realize and what are the platform existed already, and what is the important that the platform which we are establishing, what is the use of it. So the most of the platforms are done in a like a free space or with some micro nanostructures, and let's say that if you trap an atom in the cavity, then it can work as a single photon. This is typically how does it looks in the microcavity with a 10 micron. And also some of the works by the Stanford University by like having a trap the single quantum dot in the microcavity, and or the quantum emitter on the plasmonic nanostructure, and also to collect the single photons. And the platform is that you have a solid immersion lens, and is also some of the people have demonstrated the photonic crystal works. So these are the already existing platform. So what is so interesting in the fiber inline platform is that, so the problem with this all platform is that when you are trying to integrate the existing fiber networks, it doesn't fit into that, because the mode which is coming, it's a single photons throughout the one of the mirror, either this side or this side, it does not readily integrate into the fiber. So for the structure itself, you can see that how it is. So, and also here also, when it is integrating into the fiber, so there should be an automatically integrated. So there should not be any mode mismatch between the any existed manipulated the quantum mode, quantum emitter. So the mode which is being coupled to the cavity, that should not be disturbed when you are integrating into the fiber. So there will be huge mismatch, the photons which are being emitted in a particular cavity mode and to the coupling to the fiber. So for that reason, it's like a existing fiber already inline platforms are that if you have a nanofibers, what it can do is that you take a conventional single mode fiber and taper it down to the nano, then that's already in line with the fiber. So you don't have to do much or any other optical components. You don't need to kind of integrate into the existing fiber networks. So you pick up one part, I mean, in the center part of the fiber, any area, then you heat it and pull it down to the micro or the nano scales. Then you can, since the structure itself is very small, so it can effectively manipulate the single photons in the photon emitter. If you place on the surface, then it can efficiently manipulate. These are the all existed platforms at the as of now in the fiber inline. So that right now, then the internet which we are getting is through the fiber cables, right? So if you functionalize the fibers in a quantum, so that can be utilized for the all quantum applications like a fiber coupled single photon sources, and also the quantum sensors and all this stuff. So that's the line which we are working. So then there are other cavity platforms that if you the coupling to the single photons into one direction, that also has been proposed and established, then what we are proposing in our this thing is that it's like in order to have a maximum interaction with the emitter with the fiber mode is that when you place a emitter inside the fiber, this proposal was done from the Max Planck some time back, that they use a conventional fiber and they made a hole through the fiber and they can see the interaction of up to 18%. So in order to further enhance the interaction, so what we have done is that the whole structure, we made it in our simulations, that if you make the whole structure is a nano, and the center part is a nano hole, then you can kind of enhance the interaction of up to 52%. This is the half of the photons are being coupled into the fiber mode, which is a promising number. So then we have simulated and we have seen that what kind of parameters, it depends on that the inner diameters of the, we are talking about in the 50 nanometer to the 250 nanometer, and the outer diameter of the about in 400 to 600 nanometers. So the maximum is at this place. So where we are trying to realize the such parameters experimentally, and let's see what kind of developments we are doing. So this is the without cavity. This please do also mention that this interaction we realized without keeping any cavity. So obviously that if you keep a cavity, which is a different from the existed conventional technologies, is that the cavity fabrication is done in the other substrate, and this is the fiber which is coupling the single photons, which is what we call it as a nano capillary fiber. So if you don't integrate with the periodic structure, so you don't form a cavity. If you integrate with a periodic structure, so you form a cavity. Then this is the typical standing wave. How does it? It gives that cavity on the nano waveguide. So we have optimized the various parameters of the cavity, and we could realize that the maximum coupling into the fiber mode is 87%. And currently we are limited by the scattering loss. In most of the theories, what we have done is that they have not assumed the analytical expressions. I mean to say that they have not assumed the there is a finite loss introduced by these cavity structures, because the light is due to the scattering from these structures, the light is coming out, so it is not efficiently guided into the fiber mode. So we could maximum you could get it about 87%. It's a very significant number to kind of realize a cavity-QED platform as a single photon source. So this is everything was done on the nano waveguides, and there is all the parameters. You can see how much freedom you have, that even if you fabricate the 100 nanometer to 150 nanometer, your interactions remains the same, but however the resonance wavelength is getting changed. So these are the cavity characteristics we analyzed, and this is the for the X and Y polarization. So that because in the quantum applications, you should have a definite polarization to kind of encode the information. So our cavity responses for the X and Y polarization, this is the left is the X and Y, and we further analyze the cavity, this thing, to get a cavity-QED parameters, which is what we call it is a cooperativity and the single photon coupling rate. And these are the maximum finesse and the maximum the Q factor you can achieve using the our systems. So normally the finesse is that how many round trips the photon makes before exit the cavity. So it's about 378, which is conventionally finesse was shown that you should have a more really high, like in the more than 1000 or the 2000, because in the conventional systems you don't have a transverse confinement by the nano waveguide itself. But in our case, the finesse of like a 378, it could give a good interaction. So with a smaller finesse, we could realize a good cavity structures on the nanofibers or the nano waveguides. So this is the, as I said, the cavity-QED parameters. Conventionally in general, people talk about the Purcell factor and the cooperativity, which is a 2Z0 is a single photon Rabi frequency. Depending upon the type of the emitter you choose, that your single photon Rabi frequency depends on that. So suppose if you see you see this cooperativity, which is a depends on your single photon rapid frequency, and also it depends on the kappa, which is a cavity field decay rate, and also gamma, which is what you choose the spontaneous emission decay rate of the emitter. So depending upon the purpose, we can choose one of the quantum emitter and go ahead with the experiments. As of now, we are using 3 emitters in our lab to demonstrate these experiments and see while going through the experiment what kind of difficulties we had. So because it depends on the emitter you choose, your gamma is different, therefore your single photon rapid frequency is different. So then how to generate a single photon? This is the people often have a confusion. They think that if you have a attenuated laser pulse, then you can get a single photon. But the schemes what we are talking is somewhat different from the getting a single photon from the laser pulse itself. That most of the kind of some of the experiment, or I would say most of the experiment, they generate a single photon from the attenuated laser pulse. Actually, the real single photon should exhibit a subposition in statistics. But when you pick up the attenuated laser pulse, it will give a the statistics remains the same no matter what you do to that. So it's like this is a Poissonian distribution from the laser. So if you take a distribution and attenuate, so it will be remains a Poissonian. You will never reach a sub-Poissonian statistics. That's the important point should be mentioned. Then how do you generate a real single photons? If you take an atom that you have a ground state 2-state atom, then ground state and the excited state, then you excite the atom, it goes to the upper state, and the subsequent emission would be a spontaneous emission, then that will be a single photon. Please do understand that it's a single atom, which what makes the experiment is quite difficult to get. Often, most of the experiments are done with the millions of atoms, often. So, and that is a challenge what we have in an experimental, and see how do you overcome that. And what are the candidates to kind of realize this kind of a scheme, that single atoms or single ions or the single molecule. So these are the 3 candidates you have to realize a single photons. And also recently the single color centers in nanodiamond, which is a variety of color centers, the nitrogen vacancy centers or the silicon vacancy centers or any other vacancy centers are getting popular nowadays. And also the semiconductor quantum dots. The single semiconductor quantum dots are also serve as a single photon sources. And recently 2D material is becoming a good platform for generating the single photons. So when we choose a single atoms, trapping a single atom is quite challenging and requires quite a lot of intense amount of money and also intense amount of kind of expertise you need. And it's similar with the ions and molecules as well. So therefore, what we have chosen is that the other solid state emitters, where you can realize somewhat a reasonably good funding, we can do the experiment. So we have chosen the color centers in nanodiamond and also semiconductor quantum dots. The advantage by choosing the solid state emitter is that they can be easily manipulated and they can be placed wherever the photonic environment you would like to place, because they don't fly and they simply stick to the structures and you can perform the experiment. Whereas the atoms or ions, they are always flying in the air. So when you try to kind of cool down the atoms to the cryogenic or even less temperatures, still you cannot stop the movement of the atoms. So if you want to place a precise location in the nanophotonic structure, it's quite difficult. Still, it's an atom, because atom never comes to the rest, either ion. Okay, that's where the challenge lies. So in our lab, what we have is that you have a colloidal single quantum dot, the quantum dot solution where the millions of quantum dots are there. And also we have the nitrogen or the silicon vacancy centers in the nanodiamond. These three different emitters we have. So as a test, we are doing the first experiments with this, which I am going to show you. Then we are continuing the experiments with this thing. So when you make a choice of the emitter in the solid state, so we have to be careful of these three things, because when you choose an atom is the emitter, so obviously you know that it's a unity quantum efficiency of the system. Because if you give one photon to the atom, one atom, you're guaranteed that you will get the one photon out of the atom. But whereas when you choose a solid state emitter, there will be always a loss of a photon in the other channels, which is a non-radiative decay channels. It's not necessary that it will be radiatively decay. There will be a non-radiative channel in the when you're choosing the solid state quantum emitter. In this, often this is the kind of situation. Then when you have a high quantum efficiency, that means that near to let's say 95 or maybe 97%, then you have a less non-radiative decay. So predominantly by the more than 95% of the you guarantee that you get a single photon. This is one of the challenge with the solid state emitter. And also, when you choose the solid state emitter, so you should be having a fast decay rate. So because when you want to store the information, so when you excite the atom, it should come as soon as to the ground state so that you can store the information in the next cycle. So it should be fast, the decay rate. So when you choose the emitter, they should have a fast decay rate. And the important thing is, like unlike the atom, if you take a Fourier transform of the decay rate of the atom, so obviously you will get the Fourier transform limited line widths. But in the solid state emitters, you don't get a Fourier transform line widths. So because there is a spectral broadening exists always due to the phonon contribution or due to the spectral diffusion or this spectral effects. So therefore, when you choose emitter, you should be careful that the narrow spectral line width should be maintained. So that the emitter, we have the silicon vacancy centers is nano diamond at the room temperature is shown the state of art photon emitter in the present market. But however, it's quite challenging to do the experiments and to realize a single photon. Still, we are working in that regime. So as I said, that these experiments are really challenging because we are structures which we are making is like a 1/100th of the human hair size. So therefore, we need really kind of careful about the handling the structures and all the stuff. So before we get a funding, so we first started with a simple chemical etching. So this is the conventional single mode fiber, and we place it in the HF liquid. Then we etch it. Then we can see that you can get a 500 nanometer structure, so that you can manipulate the single photons. So these are the using the chemical etching. So this method has a disadvantage that you can see that the fiber surface has a lot of tiny structures which will affect the single photon propagation through the fibers. But however, so using this technique, the developed one, so we could fabricate the nanofibers. Then next, when we get the funding, so this is the unique mission, I must say that first of its kind in the country, that we develop to kind of realize a very high quality optical nanofibers. So idea is very simple. So we use very high purity oxygen and hydrogen. We control very precisely the flow rate of both the gases, so that we will make a very small micro nozzle. So here you can see this is the micro nozzle where you can make a uniform flow, and the fiber is being placed on the high precision stages, which is placed here. There is a V groove. Then the fiber is melt up to 1200 degrees centigrade because it's a melting point of the silica. This is the SiO2. Then there is another stage which is coming precisely maintaining the heater position with respect to the fiber. So to develop this technique and develop this whole optimize the parameter, we almost took 2 years to establish this facility at our place. And now in our case, what we have optimized in such a way that everything is controlled by the computer. Only thing human interference will come just to place the fiber on the stages, and you run the just click the start, and it will pull by this pulling parameter. At the end of it, just you collect the fiber what is required for your experiment. This is what we have designed, and we took some time to kind of establish this facility. So this is the thing, as you can see, video is. So this is the 2 stages, and this 125 fiber is placed, and the other one is bringing the heater. This is a micro heater. So then you realize that this is the nanofibers. So how do you verify that whether you get a nanofibers and microfibers with very high high quality fibers? So when we collect those samples and we put it under the electron microscope, you can see that the fibers are really uniform. The diameters you can realize. So you see this, the diameter variation, which is very uniform compared to any other method exists. So the reason is that we are generating the flame. It's a really high quality flame because the gases are very high purity, so we don't get any dust in the flame, and also the fiber is pulled very systematically, so that the surface smoothness is almost the uniform. So you see that if you measure the couple of fibers and you see the diameter variation, almost you can get 500 plus or minus 20 to 25 nanometer diameter. So such high uniformity we can realize. So then the next challenge would be that how do you manipulate the single photons? So as of now, we have seen that we can make a good fiber platform. So these fibers these fibers can be used for the experiment. Importantly, I must say that the throughput through the fiber is you can get more than 95%. Even if you perturb the fiber to the 125 micron to the smaller, so you can the throughput through the fiber is still maintained more than 95%. That is the important point of the technique, this one. So then you should be able to manipulate the single photons, right? So we should bring the single photons on the surface of the fiber so that you can effectively collect the single photons. And what we have developed is, it's what it's called micro and nanofluidic technique, that we first prepare a nano tips. The idea is that you have a chemical etchant, it's a HF, then you just dip the fiber tip into the HF, then you can realize the good quality of the nano tips. So while doing the experiment, after finishing the etchings, first we optically characterize them. What is the throughput through the fiber, throughput through the tip? Then you can see that very clear diffraction pattern. Then the optical quality of them is, most of the cases are more than 60%. Then we plug into the FESM image, that is the electron microscope. Then you can see that you have the tip sizes of varying different tip sizes are realized. So you can see that you can realize up to like 178 and from the 820 variety of the tip sizes are realized. So most of the cases you can get less than 500 nanometer. The question comes, why do you need such small tip sizes? So this is the, as I said, that as we are developing the small like manipulating the single photons, the idea is very simple. In our case, the colloidal quantum dots are existed in the solution. It's like you have millions of quantum dots in the solution. Then you need to pick up one dot from the solution. So if you have a nano tip, what it will do is that it is like a nanospatial filter. How do you usually do? Actually, if you want to pick up a one dot, so you should have a very small spatula so that you can pick it up a very tiny amount of a liquid, right? In reality, we don't have such accuracy. So therefore, what we have done is that the nano tip itself is act as a spatula. So when you dip into the solution, because the tip size at the end is very small, that it will pick up only the very tiny droplets. That is, we estimated it's about a sub-picoliter we can pick it up the solution drops. So the quantity. So therefore, what we have done is that only the challenge is that when we are how do you make sure that when the tip touches the surface of the liquid, not to dip into the fully into the solution. If you're fully into the solution, you pick up more than the solution what was required. So for that, the idea is that you send a laser through the tip, then make sure that the tip is being retracted when tip just touches the solution and it is being retracted. So how do you make sure that? So because when you send a light, there is a refractive index change when it is reaching to the surface of the liquid. Then if there is a refractive index change, then you can retract the tip. That means that the tip has been touched the surface of the liquid. That's the idea what we are doing. Then you can see that as of now, this stage is not motorized. Manually, we are moving. So because of the funding constraint, we could not motorize. But now we are working on motorizing and everything, making precise, so that we are able to kind of do precisely dipping into the solution. So we can see that when the tip is touched the surface, then you can see the scattering, then it is being retracted. So that's the idea, that how do you kind of manipulate a quantum dots at a low number. So then you know that there is a quantum dots or it's being dipped into the solution. So then it must be characterized optically, so that you know that what kind of a quantum sources you have, whether you have a classical source or the quantum source. So therefore, what we have done is that we excited the tip optically with a 532 nanometer. Then these the photons which are being coupled to this tip fiber modes are measured spectral information as well as the timing information using the single photon counters. So we see that the photon counts from the tip, the finite counts. Then you see that there is a background from the tip as well as the stray light. And you can see the definite photon count. Then, as I said, that for the real quantum application, you need a really narrow spectral line. Since we are working with the quantum dots, it is expected that it exhibits the spectral width of about 10 to 50 nanometer. So this is the spectral information, and this is the photon counts, how many it's coming. So, but still, it does not say that whether you have a quantum source or the classical source. As I said, for that we need to establish a Hambre boundary setup, which we already shown in the beginning. That often people think that if you detonate a laser pulse, which I already discussed in the some time back, that you can get a single photon, but no. So because no matter what you do, you cannot get a single photon. Because if the laser pulse is placed, sent through the Hambre boundary setup, which is basically 50-50 beam splitter, then the one channel is photons are detected at D1 and other channel is detected at D2, then you measure the photon correlation. So if you have a single photon, so once you send to the through the 50-50 beam splitter, so it will be detected either D1 or D2. It cannot be detected at D1 and D2 simultaneously. So that's the point. So when you send a single photon, when you take a correlation between the D1 and D2, you would see that the correlation is 0. Okay. So, but whereas when you send a laser, so there will be a finite probability that you have 2 photons. When you send a laser through this, then one photon is detected here, other photon is detected here. Then when you take a correlation, there will be a finite correlation. There won't be at 0 delay. There is no 0 correlation because there is no correlation for the Poisson statistics. So therefore, if somebody says that you can generate a single photon or you can get a sub-Poisson statistic single photon sources from the laser, that's not quite correct. So single photon means always you have a single photon. So there is no multi-photon probability. Always you are definite that in this cycle you have a single photon. The next cycle you have a single photon. When you take a laser, as you know that Poisson distribution is that 0% probability is more compared to the 1 photon probability. And 1 photon probability is more compared to the 2 photon probability. So that's the Poisson distribution always is in this kind of things. Okay, so for the laser, so attenuation of the laser would not give you really the single photon. So then when you correlate and when you perform the correlation, which is a Z to tau, then as I said that for the Poisson statistics, you don't see any correlation because they are not they are not generating a correlated photons, which is a single photons. So whereas when you measure for the photon correlations for the single photon sources, you see that you have a very strong correlation. It's a zero delay. You have a as I said, if you have a single photon, it cannot be detected D1 and D2 simultaneously. So either it will be detected D2 and the D1. When you take a zero delay, the correlation, you would see it's zero. So this is the true quantum nature of the photon. By measuring the photon correlation, it will judge you whether you have a Gaussian statistics and the sub-Gaussian statistics or the super-Gaussian statistics. So here, if you see a flat line, that will be a laser, which is a Gaussian statistics. If you see there is something called bunching, then you see that is a super Gaussian statistics. This is the setup which we make, which we took some time to make this setup. Everything was, it's not commercially available ready. It is available, but it's very expensive. So we built ourselves that so that it can be cost effective at our place. So we could build very cheap in compared to the commercially available systems. So only what you need is that you need a basic optics, and also you need a good photon correlator, and you need a two single photon counters. Okay, so with this, so we could generate the kind of a correlation setup where you can really measure the photon correlation from the single photon source. So these are the two detectors. It will be detected from the one is the transmission side, another one is the reflection side, and this is the correlator, because the single photons are detected and it has to be correlated and it has to be connected through the these things to the photon correlation, and you can see the correlation here. This is what we have established in our lab. Here I must mention that this is the Ambry boundaries we developed. That conventionally most of the people use 1-inch optics to kind of do the experiments. In our case, if your beam size is a few millimeter, you don't need a 1-inch size of optics, which is also further reduce the cost of the equipment. So this Ambry boundary setup, you can even move from the one place to another place, and so that you can perform the correlation wherever we kind of wanted to do the things. So as of now, we are acquiring the data to kind of do the experiments. Still, it is under going. So that, thank you very much for your attention. I would be very happy to take any questions on this. I hope I am on time.
Yeah, you are perfectly on time. Questions? This is really fascinating that you have one photon at a time. Huh?
Yes.
See, for example, you showed diffraction pattern. Diffraction is a wave phenomenon, right? So if you have a very single photon, how do you see diffraction?
Yeah, honestly, we have not yet measured for this pattern for the single photon. We are still yet to be done the experiment. What we are kind of expecting is that if you have a one photon, it is like a 1 pixel on the CCD. By sending the continuously single photon, we would be able to kind of reproduce this pattern when you send a bunch of light through the tip.
Yes.
This is what we were expecting, but honestly, we have not done the experiment with single photon as of now. So we are, as of now, we are characterizing the tip by sending the laser light, as I said. So laser light cannot be treated as a single photon source. So therefore, I don't say that it's attenuated laser light still gives the same thing. But what we are hoping that in future, once we get the single photon and we can send it through the tip, then sending the continuous single photons, it should make the replicate this all the patterns on the screen.
So that is very interesting. And I have one more comment. You know, recently there is a we have done some work. There is a Nature Photonics paper 2025. I've sent you the paper. You know, there is an exact priority relation. You know, this coherence, which path and entanglement, they add up to 1.
Okay.
that would be a way to check, you know. So I will, send you that paper. This is very nice to see after so many years, somebody really verifying our paper in laser photonics one.
Yeah.
This standard double slit, triple slit kind of experiment. I've seen you that paper.
Right.
Curious to see if wave particle duality that can be used to characterize single photon source.
Right. So
Very
those
nice.
experiments are easy, sir. Actually, once you have a fiber coupled single photon source, so you can basically send the single photons into the slit, and we can record the pattern. Yeah.
Now, just one more thing. See, for example, have you used your apparatus for like sensing kind of thing?
Okay. That is what we are kind of targeting. Yes, the emitters which we are, as of now, as I said, as a test, we are using the quantum dots. So now we are moving to right now we started working on the nitrogen vacancy centers in nano diamond. Then we are kind of developing the things, not yet done the experiment. Once we couple this nano diamonds and nitrogen vacancy centers in nano diamond to the fiber, it can work as a fiber-based magnetometer. So we are trying to couple, and we see how much field we can sense it actually. That's what we are developing that setup actually as of now. So in future we would like to do like a fiber coupled magnetometer. So for that you need a spin manipulation setup which we are establishing. So we need a microwave sources and all other stuff so that we can kind of manipulate the spin in the NV centers, then which is being fiber coupled. Because when you have the probe to the such nano, so you can kind of access any it's like a local probe sensor. So conventionally people sense it's like a very big structures. So real local field nobody knows. Actually, it's but if you make these kind of sensors very tiny, so you can easily know the real local field strength. That's what in future we are planning. Yeah.
See, it will have application for biophotonics, like cancer tissue, normal tissue, growth of cancer, those kind of things.
Right.
Very nice. Other questions, please?
So much. Yeah. If you have any questions from the students.
Actually, what do you mean by single photon?
Hello?
What do you mean by single photon?
What I mean by single photon. Thank you.
Consider it is a field.
It is, I think I gave. Okay. It's a thing like a single photon pulse. Can you see the screen now?
We see the screen, but I don't get the screen.
Suppose if you have a atom in the ground state, right?
Yeah.
To excite, then the atom has to be de-excited, right?
Yes.
And it will come to the ground state, then it has to lose the energy by emitting a one photon. But only thing I want to tell you that this has to be a single. You cannot have a collection of atoms.
Okay.
So suppose you send, let's say that you hold on, just suppose you send a pulsed laser, okay, like this. Now you should also get single photon pulses in every excitation cycle. Okay, but if you have two atoms here, so you would expect to see that you don't see single photon pulses, you see multi-photon pulses. Single photon probability is low if you have two atoms. So that will degrade your quantum nature of the photon. Even if you go to the real quantumness is, as I mentioned, that here when you have two atoms, let's say two atoms, then your zero delay, you would not see 0, you would see 0.5, because detecting the the photons, not the 0 at the 0 delay. I mean to say, if you have a two atoms, the one photon goes here and another photon can go here. There is no 0 probability that other photon comes here, because you have a two photons simultaneously. That's the point. So therefore, you will have a 0.5. Then you have a 10 atoms. Then you're coming to the kind of classical regime, not anymore in the quantum regime. If you increase the n more, so then you are going to get into the classical regime. Is that clear?
Okay. Yes.
Okay. Thank you so much.
Sir.
Yes, please.
I think there is a question from the audience.
What was that? Can I read?
Yeah. Sir, there is a question from the audience. I have a quick doubt. When you meant indistinguishable single photons, it has to be indistinguishable in which degrees of freedom?
No, I am saying indistinguishable in the frequency. Frequency of the photon has, I mean, okay. Hold on. So when you see that when it is being emitted, the spectral line width of the emission, that single photon it comes, it is limited by the decay rate of the excited state, right? Normally, if you have a decay rate of, let's say you have a 30 nanosecond decay rate, which is a spontaneous emission decay rate of the atom, let's say, then the corresponding line widths you get a megahertz. But ideally, in theoretical also speaking, that you don't get at a single frequency the single photon, okay, because it has a finite width. When it comes to the experiment, when you choose the in our experiment, when you choose a quantum solid state quantum emitter, you expect to see the spectral broadening, which is not Fourier transform limited, because there is other contribution which is coming and contributing to the broadness of the spectrum. So when you say ideally the lambda is your the emission comes, but in reality it doesn't come at lambda. Lambda plus or minus delta lambda. So one photon comes at lambda, other photon comes at delta plus lambda, another photon comes at delta minus lambda. So therefore, if you want to have a really high indistinguishable, so you need to have that delta lambda has to be very, very narrow. The theoretical limit is that, that is the fundamental limit is that you cannot beat the excitation lifetime of the emitter. So when you have a 30 nanosecond, you are expected to see 30 like the 5 megahertz line width. You will not get 0 megahertz. Anyway, you will never get. But in the solid state emitter, that is a more serious. So because that you don't get megahertz, you will get gigahertz line widths. So because there is a contribution from the phonons and all the things. Of course, if you are working at cryogenic temperature, you can further get it down, but still. But the only way to kind of tell that how much of indistinguishability you have in the source is that you need to perform, there is something called Hongo-Mandel experiment. That's what we are trying to extend that one. But here, see, we are doing one by one. So here itself, we can, in the setup, we are trying to establish for the Hongo-Mandel also. You need to develop similar thing and further one by placing here, so that you can kind of interfere two single photons which are coming. Then you can measure the visibility of that. So which kind of in future we want to do. That is in this frequency, we are saying that it is indistinguishable. Ideally, you want single photons to be a same wavelength all the time. But in reality, that will not happen. That's what I'm trying. Is this question clear?
Yes, sir.
Okay.